Hello, how's it going? Welcome again to Calculus. So, we got done with implicit differentiation, and we ended with kind of that weird example where we said instead of having just x and y, we had x was equal to x of t and y was y of t. So they were two kind of functions within functions. And now we're going to get to what is one of the coolest applications of calculus that we've seen so far, and that's related rates. In related rates, I could literally spend the next hour telling you all the applications of related rates, but instead we're just going to dive right into it. It is a direct application of implicit differentiation. So let's get to it, shall we? So, we've got a balloon. It's a spherical balloon, and air is being pumped into it at a rate of 5 centimeters cubed per minute. At what rate is the radius of the balloon increasing? The radius, remember, is the center to the outside, when the diameter of the balloon is 20 centimeters. All right, so let's set up a little method. It seems like there's a lot of information here. Who knows how to get started? First off, what info have we been given? Well, we know that the radius and the volume, they both increase with time. So that means we have radius and volume change, it's an in, with time. So they are, as you might expect, r of t and v of t. Okay, great. What else do we know? What do they tell us here? They tell us that it's being pumped into the balloon at a rate of 5 centimeters cubed per minute. Centimeters cubed, you know from that cube, that's a volume. And then per minute, well, per minute means that is volume over time. That is the change in volume with time, which our calculus brain tells us means it is the derivative of volume. So we know that v prime of t, the change of volume with time, is equal to 5, right? And now, another thing we know is that we are looking for the answer at a time when r, well, let's see what they give us. They tell us the diameter of the balloon is 20 centimeters, so that means the radius, r, is going to be 10. Okay, so that's kind of what we know. Next, what do we want to find? Well, we want to find, they ask us, at what rate is the radius of the balloon increasing? That's our question, the rate that the radius is increasing. Well, that sounds to me like we want to find r prime of t. That's the rate at which the radius is changing. Okay, and we want to find that at the point when r is equal to 10. Okay, it's all pretty comprehensible so far. What is our relation equation? What does that mean? Well, let's see. We have a known thing, the change in volume with time, and we have an unknown thing, the change of r with time. Well, let's see. Let's go ahead and try to write an equation for this. So let's say the volume of a sphere, v of t. You know what? Let's just say, for simplicity's sake at first, v equals, you know this equation, 4/3 pi r cubed. That's the volume of a sphere. And now we're going to introduce an element of time. The volume at any time t is 4/3 pi r of t cubed. All we did was take these two variables and introduce an element of time to them, right? All right, step 4, do some calculus. Okay, what do you think we're going to do with this equation? You're right, we're going to take the derivative. And the derivative of this is quite easy. So v of t, remember, that has an inner function, v. So we call this the blob. What is the derivative of blob? Well, it's just 1. And then the derivative of the blob itself is v prime of t. Okay, now we have 4/3 pi. That's going to stay where it is. Now we have this. This is our blob. Blob cubed is 3 blob squared, and then times the derivative of the blob, which is r prime of t. So this cancels with that. And what do we have for our final answer when we tidy it up? Well, we have 4 pi r of t squared times r prime of t. And let's go ahead and drop these of t things because you get it now, right? Right? I hope so. 4 pi r squared r prime. Isn't that nicer to look at? Okay, so that's our relation equation. This is our relation equation. This is our relation equation, the derivative of it. Now, this looks a little overwhelming, but check it out. What do we know? We know that v prime of t, v prime is 5. So we know that. 4 pi, those are just two numbers. We know r was 10. And what are we trying to solve for? We're trying to solve for the rate of the radius changing. That's r prime. Let's just rearrange this equation real quick. R prime equals, divide by that, v prime over 4 pi r squared. All right, well, volume is 5. We have 4 pi, and then r was 100. Or, sorry, r squared is 100. Okay. So that means that if you simplify this all down, it turns into 1 over 80 pi centimeters per minute. So I just want to go through that. We were given this balloon. They said the volume is changing at this rate. What rate is the radius changing at a certain time? We write down what we're given. We write down what we want to find, which is this, r prime. What is our relation equation? This is the hardest part of all of these. You have to find the equation that relates what you know to what you don't know. And it's this one, volume of a sphere. We do calculus to find the change in volume of a sphere as it expands. And then we plug in and we get our answer. So good. Basically what we're going to be doing today is a bunch of examples until you know this so disgustingly well that you just want to throw up all over your keyboard. But hopefully you won't, because you'll be so satisfied with yourself. The units of the answer were in centimeters per minute. Do you remember this? We said r prime equals 1 over 80 pi centimeters per minute. So how do we get these? Well, we know logically, we are finding the rate of change of the radius. So radius is measured in centimeters, and then rate of change is going to be, we're talking about minutes, so it's going to be centimeters per minute. You could also look at it as r prime is dr dt. That is centimeters, that is minutes. All right, next example. A 15-foot ladder rests on a wall. The bottom is initially 10 feet away from the wall and is now being pushed towards the wall at 1/4 feet per second. Let's draw that out real quick so we know what we're talking about. We've got a ladder and it's leaning against a wall. Okay, so it is, what did they say? It's 15 feet long. That length doesn't change, right? The bottom is initially 10 feet away from the wall and is now being pushed towards the wall at, we're going to call this x prime, because this distance here is x and this is y. So x prime is 1/4 feet per second. How fast is the top of the ladder moving up the wall? Well, that's going to be y prime. And how fast is that moving up at 12 seconds? So let's see, we have our x prime, we know. This is x, this is y. X prime is equal to 1/4. Okay, so what is our x? Let's see here. If our x is this, we know that we started at 10, right? So we know that, well, let's see. What am I trying to say here? I want to phrase this in a way that makes sense. Let's just say this. Distance is equal to rate times time, right? So like meters per second times seconds, so the seconds cancel out. All right, so if we have the rate, 1/4, and then do we have the time? Why, yes, we do. How fast is it moving up the wall at 12 seconds? Well, that just gives us 1/4 of 12, and that is 3. So we know that x is 3. And for y, could we find what y is at that point? I bet we could. So how would we solve that? We know that you have this is a right triangle, right? Walls are straight up and down. So we could say that when x here is 3, oh wait, no, we need to be careful here because we've only moved 3. So that means that at this point, x is going to be 10, which is the original length, minus 3. We've come in 3. So x is equal to 7. Hope I haven't confused you too much here. We calculated that the thing has moved 3 meters. That means it started out 10 feet away from the wall. It's moved 3 meters, now it's 7. So what we could do is we could say 15 squared, that's the hypotenuse, equals 7 squared plus y squared. And that's going to find our y. So first of all, 15 squared, what is that, 225? I'm going to pull up my calculator here just because I like to, when I'm getting tired, make sure. 225, of course, should trust myself, equals 49. Okay, so 225 minus 49 is 176 equals y squared. So y equals square root of 176. Let's just leave it at that for now because I don't think that has a square root that's clean. All right, so what do we want to find? Well, let's see. We want to find how fast is the top of the ladder moving up. We want to find y prime when y equals 176, when x equals 3, and when t equals 12. What is our relation equation? Well, I think we might have already found it. I believe that our relation equation could just be 15 squared equals x squared plus y squared. That's the Pythagorean theorem. We got hypotenuse equals x squared plus y squared. So let's do some calculus. this was 225, must be off the page there, 225 equals x squared plus y squared. So let's take the derivative of that. We've got 0 equals the change in x, which was 2x, and then we do x prime, plus 2y, y prime. And again, remind yourself always, what are you looking for? You're looking for y prime. So let's go ahead and solve for that before we do anything else. Let's say, bring this to the other side. So now we have 2y, y prime equals negative 2x, x prime. All right, we're going to divide by 2y, divide by 2y. 2's cancel out, and you get y prime equals negative x, x prime, y. All right, and let's see what happens there. So we solve. So what do we know? Do we know x? Yes, we do. X is 3. No. X is 7. I didn't correct that up there. Aha. Lessons all over the place. Definitely stay organized with your corrections if you mess something up. Y prime equals negative 7 times 1/4 for x prime, and then over y. And what was y? It was the square root of 176. So that reduces to 7 over 4, 176. And one thing I notice here is that I have a negative. Now where did my negative come from? I subtracted over here, and then, but I know, do I know? Okay, this is another good lesson. So I've obviously done something that's given me a negative. But then I look and I say, okay, how fast is the top of the ladder moving up the wall at 12 seconds? Well, if a ladder's moving up like this, is it going to ever be negative if it's moving up? No, it's going to be positive. So I'm guessing that what I've done here is introduce some negative. I know I did it here, but what I'm going to do is just use my common sense, and I'm going to say that it's positive. So the answer is 7 over 4 over square root of 176 feet per second. Is it perfect? No. But does it make sense? Yes. And so that's what I care about. I care about knowing that our answer is logical. And I'm not going to bore you with going that and troubleshooting right now in this video. We're going to keep moving. Alright, so let's check this out. Two people are 50 feet apart. One of them starts walking north at a rate so that the angle shown below is changing at 0.01 radians per minute. So the two people start here. They're 50 feet apart. One of them starts walking north at a rate at which this angle is changing at 0.01 radians per minute. What rate is the distance between them changing with the angle, when the angle is at 0.5 radians? Okay, so what do we know? Well, let's see. We know that theta prime is equal to 0.01. We know that theta, at the point we're interested in, is 0.5. So let's see. What are some relationships here that we could use? Well, there's Pythagorean theorem, but we've got an angle. So why don't we instead use something like, well, there are two ways to go about this. We could say the cosine of theta, remember cosine is equal to adjacent over hypotenuse. The adjacent side is 50 over h. Or it might be more convenient to say the secant of theta, which is just the inverse of cosine, is equal to h over 50. Which is easier to differentiate? So obviously when I look at this I say, oh, cosine's way easier, that's just negative sine. However, this is where you kind of gotta think ahead. Let's look at this secant theta equals h over 50. What is, if we take the derivative of this, what is the derivative of secant? Well, it's just secant theta tangent theta. Is theta constant? No. Theta is just its own function. So we got to do chain rule. Okay? And that is equal to h prime over 50. Now notice that we did not get any h's in this equation. If we had done cosine, the h would have been down here, so you would have gotten on this side, you would have gotten negative sine theta, theta prime, and then you would have gotten negative 50 over h squared times h prime. And that would have been more annoying, right? Well, let's see. So this is great. This is a nice formula. So at this point, what are we interested in? We're interested in h prime. So let's just rearrange, bring the 50 over here. So 50, and then I'm just going to put the theta prime times secant theta tangent theta. What do we plug in? Well, we know that's 50. Theta prime was the rate of change, which is a constant, 0.01. And then we have the secant of 0.5, and we have the tangent of 0.5. And I will solve the mystery for you because I know you're dying to know. That equals 0.311 feet per minute. So, using related rates, we were able to basically sketch this out, use geometry, and figure out what is the relationship that related our known, which was the angle, to our unknown, which was the change in distance. And as I said before, the hardest part is coming up with the relationship between the known and unknown parts of the problem. And that's the part where you really can make your life easy or you can make it awful. So, always try to make it easy. Think ahead. Let's do more. What do we have now? Oh dear. There's a conical tank. That's conical, not comical. And it is leaking at a rate of 2 cubic feet per hour. The base radius of the tank is 5 feet. That's up here. Here's the base. And the height is 14 feet. So at what rate is the depth of the water, that's this h, changing when the depth is 6 feet? Now, wait, they say the depth of the water when the depth is 6 feet. Wait, no, they say what rate is the depth of the water changing? So what we're looking for there is h prime when h equals 6, right? Okay. Now, I'm guessing that at this point, you're thinking, oh God, what equation am I going to use? What equation makes sense? What do we want to know? We want to know what rate is the depth of water changing when the depth is 6 feet. So something that relates h to something else. Well, let's try the volume of a cone. What is the volume of a cone? Maybe you remember, maybe you don't. Either way, you can just look it up. So that is the volume of a cone. So now we can take the derivative as we do in these problems, right? And this gives us, well, what do we have? This is just a constant. So what we're worried about here is this times that. They're both functions of their own. They're both changing with respect to t. So we got to remember that. We have 1/3 pi, and let's do this first one, 2r times r prime. Okay, that's the derivative of that, times h. Looks like a Welsh word or something. And then we have plus 1/3 pi times r squared, and then h prime is the derivative of that. We absolutely should tidy that up because we are tidy, and that gives us 2/3 pi r prime h. And then this side is already pretty tidy. Okay, so there is one issue that you will eventually find if you try to do this, and that is that we don't have enough info to find both r prime and h prime in the same equation. Those are two unknowns. So what do? We do a little thing that we love doing in these types of problems, which is get rid of a variable. Who do we want to get rid of? Well, let's see what we can relate here. Obviously, our two contenders are r and h, right? R and h, well, they relate to each other in a very distinct way, because you can take the radius over the height. The radius is 5, the height is 14. 5 over 14. Now, note that this is always going to be that same ratio, isn't it? Because if you bring it down to here, it's still going to be 5/14. It's just going to be a different size, a different constant. So what we can do is we can say that r is equal to 5/14 h. Now, isn't that cool? So let's rewrite our volume equation. Volume is now going to be seen as, well, what did we have before? We had 1/3 pi r squared h. So we now have 1/3 pi r squared, which is 5/14 h squared, times h. Now we have only one variable, and that is wonderful, because we know what h is. They gave us an h, but they haven't given us an r. All right, so let's take the derivative of that. Well, actually, no, let's first tidy it up a little bit. That is, we got 25 up top. 14 squared, it's going to be times 3, 588. Yes, 588 pi h cubed. All right, it's looking better already. So now let's take v prime, and that is equal to, okay, well, we're going to have 25 over 588 pi. Then we have h cubed. H is our blob because that's its own little function. We got 3 blob squared. So if we take 3, I'm just going to plug this into a calculator. That gives us 25 over 196 pi h squared h prime. What did I do there? We knew it was 3h squared. So I went ahead and I said, what can 3 over 588 reduce to? And I found that we can actually reduce it to 25 over 196. h squared h prime. What are we looking for? We're looking for h prime. So let's solve for it. H prime equals 25 pi h squared over 196. Wait, no, I did that wrong, didn't I? Oh no! At least I caught it. H prime equals V over 25 196 pi h squared. And so what we'll find is that we get, when you plug in, you get, well, what was our V prime? That was -2. Okay, then we have 25 over 196 pi, and then h squared. Well, what was our h? It was 6. So 6 squared. And that gives us -0.1386. And what were our units? Well, we just looked back up. They're saying, what rate is the depth of the water changing? Well, the depth of water is changing at feet per minute. Right in the nick of time. Excellent. So now let's see. We've got a part B, and we'll have to do it on another piece of paper right here. At what rate is the radius of the top of the water changing when the depth is 6 feet? Okay, do we really need to go through this whole problem again and figure stuff out? Not really. When we remember, we're asking about the radius versus the depth. Don't we have an equation? I don't know. R equals 5/14 h. That already tells us that. Yes, we do. What's the derivative of that? Well, it's just R prime equals 5/14 h prime. Now, what do? We just plug in the result from the last part. They're asking us, at what rate is the radius changing when the depth is 6 feet? Well, that was the same depth here. So we know that the rate that the height is changing is the same as the answer we got last time, which was this. So we plug that in, equals 5/14 times -0.1386. And what does that give us? It gives us -0.0495. There we go. So that's how we did part B. It's a lot simpler. You're always trying to look for ways to simplify your life instead of make it harder. Okay. So let's move on now. What do we have now? We have a trough of water. And this trough of water is 8 meters deep, and its ends are in the shape of isosceles triangles, whose width is 5 meters and height is 2 meters. If water is being pumped in at 6 meters cubed per second, at what rate is the height of the water changing when its height is 120 centimeters? All right, so at this point, this just looks like a pretty classic problem to us. Well, first thing, let's get our bearings. We know that a trough of water is 8 meters deep. Okay, so 8 meters deep meaning this way. It's 8 meters long, is I think what they should say. Its ends are in the shape of isosceles triangles. Well, its ends are like that. Isosceles means two sides are equal. And their width is 5, their width is 5 and their height is 2. So from top to bottom it's 2, from side to side is 5. If water is being pumped in at 6 meters cubed per second, that's a lot of water, by the way, at what rate is the height of the water changing when its height is 120 centimeters? Again, what rate is the height changing when the height itself is 120 centimeters. Those are two different things. That's h prime when h equals 120. Oh, wait, look at this. Do you notice that they've given us the height is 120 centimeters, but we're talking about meters cubed? Let's nip that problem in the bud. H prime when h equals 1.2 meters. That would have given us an absurdly large number. All right, so that's a good thing to be aware of. What do we know? Well, what do they tell us? They tell us that the volume is changing at 6. So that means V prime equals 6. And then we know these things. We need an equation to relate volume to height, because that's what we care about. We know the change in volume. We're looking for the change in height. So let's see here. Volume, well, just by the way things go in math, we know that if we take the area of this triangle and we multiply it all the way down the area of the depth, that's going to give us the volume of this whole trough. So the volume is equal to the area of the end times the depth. So we have that equal to 1/2 base times height, right? Because that's the volume, the area of a triangle. And then we multiply that by the depth, which is 8. I still get confused. I want to say that's length, but whatever. All right, so 1/2 base times the height, that's just 1/2 HW, right? Because we have the width and we have the H. Those are the ones we're concerned about. And we got the 8, so that just turns into 4HW. That's equal to volume. Now, here's another one of these things where the problem, I know it's tough to go through here and decipher what exactly we have, but if we had had some type of width given to us of the water, it would have been, we would have written it down, but we don't. We just see an H prime and H and a V prime. But we have a W here, so why don't we go through and just do what we did last time and get rid of a variable? He's the offender. So what we'll do is we'll say, let's say this. Look at this guy. The width and 5 relate to the height and 2. This is a simple ratio that will hold true. And notice that if you put height down here and you put the 2 up here, you'd have width over height is always going to be 5/2. So let's see, from this we know that the width is equal to 5/2 times the height. And we'll substitute that in here. So now we have that the volume is 4H times 5/2 H. And that we just combine those 2, so that's 10H squared. Look how simple and beautiful that is. That's not so bad. And now we take the derivative. Well, that's just 20H H prime. So that is our V prime of t. That's how the volume's changing with time. And at this point, it's just a plug and chug. So we're looking for H prime, so let's solve for that first. H prime equals V prime over 20H. What was our V prime? Well, it's 6 meters per second. We can just plug in 6 over 20 times, what was the height? 1.2 meters. And what does that give us? When we calculate it out, that gives us H prime equals 0.25 meters per second. So what's the point of that example? The point of that example is we weren't just dealing with a sphere or a cone or something where we know, or a triangle where we know the volume of it by an easy to remember formula. This one we had to kind of make up the formula, right? You weren't taught the formula of a trough, or at least I wasn't. And that's okay. It kind of shows you that if you can just figure out how to represent this thing with an equation, you're golden. So have that confidence to explore. Now let's look at the next one. I don't know if your brain is super tired right now, but mine sure is. And so, as I said in my early video, when the brain starts slowing down, that's when I start being extra careful, because I don't want to make careless errors. They are the bane of everyone's existence. Oh, this is a super cool one. Check this out. A spotlight is on the ground. So a spotlight's on the ground and it's shining up here. It's 20 feet from a wall. And a 6-foot tall dude is standing in the middle. He's now walking towards the wall at 2.5 feet per second. How fast is the height of his shadow changing when the person is 8 feet from the wall? Man, this looks hard, doesn't it? Well, spoiler alert, it's not actually that hard. So we want to find y prime, that is, the height of the shadow changing when x equals 12. Now I want to go into that a little more clearly. When he's 8 feet from the wall, that means, as we've drawn it here, x is the different distance between the spotlight and the man. 20 minus x is the remaining distance. So he is 8 feet from the wall. That gives us an x of 12. So we know that x prime is 2.5 when the distance from the spotlight is 12. Okay. Now let's look at this. Y over 6. Okay, that is the proportion of this wall to the height of the guy. What is that going to be equal to? Well, that's going to be equal to this distance, which is 20, over, you might have guessed it, x. And let's test that. What about when he hits the wall? That means that it'll be 20 over 20, right? Well, at that point, won't his shadow, won't this be also 6? The size of his shadow will be exactly as tall as he is. Because he's going to be right up against it, the light will just be reflecting his, or shining his shadow exactly the same size as him. So we know that equation works. Now, let's rearrange. Y equals, we'll bring the 6 up here, that's 120 over x. And now all we have to do is take the derivative. So y prime is equal to, how do we do this? Well, I remember how to do it. Do you? If we have 120 x to the negative 1, well, we just bring that negative 1 down here. That gives us negative 120 x to the negative 2. And then we remember there's an x prime. Okay, so let's tidy that up. Equals negative 120 over x squared, x prime. Now what are we looking for? I have to remind myself, I don't even remember. How fast is the height of the shadow changing when he's 8 feet away? The height of the shadow, well, that's what we're set up to solve. So negative 120, he's 8 feet away, so 8 squared. And how fast was he moving? He was moving 2.5 feet per second. And that gives us a number, 2.0 0.083 feet per second, and I will not forget that that is negative from that negative there. So that's how fast his shadow is changing. Did that problem look really hard? It did to me. So we saw there's a guy standing in the middle, so it's not just a triangle changing. But remember, if we can just set up the simplest possible equation to describe this, which is the height of his shadow over his height is going to change the same as the length of this distance over the length that he walks. And that's how we got this. So again, that was kind of the hardest part, but it's the part that makes everything easy afterwards. All right, let's do another one. We don't have too many more to go. I think we have 2 more. Yes. So let's see here. There are 2 people on bikes separated by 350 meters. So I want to give you this example problem because I looked at it and I thought this looks harder than what we've been doing. And it is a little harder. So there are these 2 people on bikes. They start here and here. They're separated by 350 meters. Could you see that? They're separated by 350 meters. And person A, he starts going north. And he's moving at 5 meters per second. So we know that x prime equals 5. And he goes, when he's gone 7 minutes, then person Y starts. He starts going down at 3 meters per second. So at what rate is their separation changing? Now, this is the separation between them. Say this guy, they started here, and he went up this far, and this guy went down this far. This line Z is the separation between them. Okay, so at what rate is it changing? 25 minutes after person A starts riding. Oh my goodness, they've given us yet another kind of trick, right? Well, what are we after? We are after the rate at which their separation is changing. Z prime. That's our question mark. So let's see here. How far has person A gone? Person A has ridden for 25 minutes. Person B has ridden for, well, this guy started 7 minutes before him, so he had 7 minutes less riding time, right? That's 25 minus 7 equals 18 minutes. Huh. Well, if person A is riding at 5 meters per second, can we just do distance times time? Let's check it out. Now, we're calling x the distance that person A has ridden and y the distance that person B has ridden. Don't confuse those with, x being this direction and y being that direction. It's not that. These are just our variables for this equation. So, x, that's the distance that person A has ridden, is equal to the distance times, or the rate times the time. So he has ridden at 5 meters per second, and he's ridden for 25 minutes. Now we're talking seconds here, so we need to multiply 25 minutes times 60 seconds, right? And that will get us our answer, which is 7,500 meters. How about person B? Well, he's riding at 3 meters per second, and he's riding 18 minutes. We're going to multiply that times 60, and that will give us 3240. At this point, you might ask yourself something. You might say, hey, wait a second, I thought we should always keep track of our positives and our negatives. This guy's moving that direction at 5. This guy's moving that direction at 3. Shouldn't that be -3? Well, it could be, but you'd have to subtract these two. Because you got to think, the distance between them is growing bigger. And if you subtracted this distance from that distance, you would be getting a smaller distance, wouldn't you? So that's why I kept them both positive. It's kind of a scalar thing. So now let's look at it. What is the relationship that is prevailing here? We've kind of got this triangle, the distance z. Let's call that the hypotenuse. Well, what are our sides? One of them, what's this side? This side here is the distance that y and x have traveled. I'm going to superimpose this bit over to here. So that is now x plus y. That's one leg. X plus y squared plus, what's the other leg? 350. Good. And so, really, this right here, oh my God, this is our equation. We've just stumbled upon it. Not using something that you learned in algebra. This wasn't an equation you memorized, z squared equals x plus y squared plus 350 squared, but by using your common sense and figuring it out. So, z squared, if we plugged in right now, we could find what the distance between them is. So we know that x is 7,500 and y is 3,240. Well, I'm just going to solve that right now. Z squared equals that plus 350 squared. Well, square root of that is 10,745.7 meters. So that's equal to z. That's not what we're after, but it is important because it gets us closer. Now let's take the derivative of this. Remember, we're always going to take a derivative because what we're looking for is we're given their rates of change, and now we're asking what the separation, how the separation is changing. So we're looking for dz. So we're going to say 2z z prime equals, now what is this? X plus y squared. Well, this is our blob. We have 2 blob times the derivative of the blob, which is just x prime and y prime. And then plus 350 squared, well, that's just 0, because that's a constant. These 2's go away. So now what are we trying to solve for? Z prime. Let's just solve for it right off the bat. We have x plus y times x prime plus y prime over z. We know what z is. We know what our x and y are. And we know what our x prime and y prime are. So we plug all those in. And it'll look like this. So x and y was 7,500 plus 3,240. The x prime and y prime were 5 plus 3. Then what was our z? 10,745.7. And that gives it, or gives us rather, what is it? 7.996 meters per second. That's how fast their separation is increasing. So look at that. That's one that you had not seen something quite like it before, and it turns out that most of it was just talking your way through it and drawing a good diagram. So let that be a lesson. You always want to draw a good diagram. All right, we're going to do one more because we've been doing things that have been geometric so far. This is our last example, by the way. And we want to try one that isn't necessarily geometric. So this is one that you're actually going to be using, yeah, you're just not really going to have a diagram even. Let's make sure I'm calibrated on your screen. Can you see everything? Yes. Okay. Once again, my ghetto setup is, it leaves a lot to be desired. All right, so we're now talking about electronics, which is a big part of physics, really is where you see a lot of this, and engineering too, I'm sure. So we have two resistors in parallel. Maybe you know what that means, maybe you don't, but the math is going to be given to you. R1 and R2, those are your two resistors, and they're measured in ohms. The total resistance of these two guys is given by 1 over the R total equals 1 over R1 plus 1 over R2. So that you might suppose that it would just be R total equals R1 plus R2, but it's not, it's that. Now, suppose that R1 is increasing at 0.4 ohms per minute, and R2 is decreasing at 0.7 ohms per minute. At what rate is R changing when R1 equals 80 ohms and R2 equals 105 ohms? Let's see. First thing to note here is that R1 prime, that's the rate at which R1 is increasing, is 0.4 ohms per minute. Now R2 is decreasing, and this is a perfect time to put in that negative 0.7, because in the last one, when the things were going apart, the total was getting greater. But in this one, this is not going to contribute to a greater whole. It's going to lessen the whole because the resistance is getting smaller. Okay, great. So now, what do we have? We have our equation. 1 over R tot equals 1 over R1 plus 1 over R2. And if we fill in for that, we get 1 over R. I'm just going to leave R total as R. We get 1 over, now R1 they told us was 80 and R2 is 105. 1 over 80 plus 1 over 105. All right. So now we want to solve for R. And I'm going to kind of spare you all the algebra here. I hope you know how to do this. You basically would find, you know what? No, I'm just gonna do it. Just because I want to make sure that people know how to do this stuff. To solve for R, you need to get R over to this side and this stuff over to that side. So bring R up here. So that's R equals, and then you're going to divide everything by this. So 1 divided by 1 over 80 plus 1 over 105. Now that's really all you need to do. Just plug that into your calculator. Okay, and that gives you 1680 over 37, which gives you 45.4 ohms. Can you see that? Barely. Good. All right, so that is your R total. Next, we want to take the derivative of this. 1 over R equals 1 over R1 plus 1 over R2. So even though you may be completely uncomfortable with electronics, you still can see that they're asking for the rate that R is changing. So you're trying to find the rate at which R is changing, which is just a derivative. Now, this is R to the negative 1, right? and that's r1 to the negative 1, and that's r2 to the negative 1. So you bring the negatives down, it gives you negative r to the negative 2, and you remember your r prime because they're all independent functions, equals negative r1 to the negative 2 times r1 prime, and then that'll be also a negative r2 to the negative 2 times r2 prime. Well, one thing we know right away is we can turn all these positive. We divide a negative 1 through the whole equation. So that's kind of nice. And let's write this in a nice way. So we have r prime over r squared, because the r to the negative 2 is that's in the denominator. Now we have r1 over r1 squared, that should be a prime up top, sorry, plus r2 prime over r2 squared. What are we trying to solve for again? I don't know. We're trying to solve for r prime, aren't we? So let's multiply everything over here by r squared. That just goes up there. Now we have r1 prime over r1 squared plus r2 prime over r2 squared. And now we plug in. I'll leave us a little extra room here. R squared. What was R? We found it. It was 45.4 squared. And now, R1 prime. What was R1 prime? 0.4. 0.4 over, and then what was R1? Well, R1 was 80. And now our R2 prime, that was minus 0.7. Minus 0.7 over, and then our R2 value given up here was 105. 105 squared. And that gives us a grand total of negative 0.002045. And that is ohms per minute. All right, that is related rates. So we've seen a lot of good examples. Definitely do the work in your book. Figure out you're going to see a lot of different examples. And the more that you do, the more will be in your arsenal, and you will be less taken by surprise when you see stuff on a test or in the future in a different calc course. Hope you've enjoyed it. I sure have, and see you next time.